All right, let's get started. So I'm going to talk about generative models and a way to compute with them called variational inference. So the really big picture of how these things work are you start with some disciplinary knowledge. This disciplinary knowledge might be like, what am I trying to predict? What kind of structure am I trying to find? What kind of data am I measuring, and how does it relate to that structure? You'd encode that into some kind of model. This is a probabilistic graphical model. More generally, it's just some code that has randomization inside of it. Once you have this model built from the knowledge, you'll collect some data, and then there's this mysterious process that happens, which is fit the model. And what you'd like to do once you fit the model is to find hidden structure, maybe a brain network, maybe something about genetics, or make a prediction, like does a person think that something is a 4 or a 5? And they've been used in several places. One example is exactly like for looking at networks inside a brain. You posit the existence of a hidden network, you observe blood flow measurements, and you want to make inferences about that network. Another example is causal inference. There's a whole line of causal inference research from observational data that takes advantage of probabilistic generative models. Another one is astrophysics. Here the goal is to take a big picture of the sky. This is from the Sloan Sky Survey, and figure out, are each of these light sources galaxies, planets, red dwarfs? And it works in a similar way. Each of these light sources have some kind of hidden structure. That hidden structure is what kind of object it is. Given that you know what kind of object it is, the physics tells you a little bit about what the light source may be, and you want to make an inference about what is the likelihood that this thing is a planet or this thing is a galaxy. Also used in genetics in a similar way. Who here is familiar with the topic model? I think there's like a section looking at topic modeling. Yeah, okay, so a small number. And so this is kind of like a topic model of genetic data, where what you get to observe are different populations. And in each of these populations, they have a bunch of genetic variations. And what you'd like to see is like those genetic variations come from mixing of populations in the past. Like one population migrated somewhere, and mixed with another, and you get a new population. And that's what these colors kind of tell you. So this is the Yoruba population. This is a Japanese population. The colors are like the different topics. Like this brown here is topic for something, and different Asian populations have different proportions of the brown that's predominantly in the Japanese. And you can use it for health records as well, too. So this is trying to do something very similar. It's a hierarchical non-negative matrix factorization on electronic health records, where you get to see the diagnoses and the medications. And the kind of hidden structure that you posit are that certain things get related into higher concepts, and there might even be higher concepts than this. So on one side, we have a bunch of things that are related to pregnancy. On the other side, we have things related to being old, geriatrics. The thing they share in common are conditions related to anxiety and depression. So what is a probabilistic generative model? Well, it starts with some data. That's what you get to observe. You have some hidden structure. I'll call it latent variables. I'll call them Z. And then the model is simply a distribution over that data and those hidden variables. Starts with a prior, so a priori, what kind of hidden structures do I believe in? And a likelihood, for the data that I see, how likely is it for a particular hidden structure? And as a really silly but concrete example of a latent variable model, imagine I get to see these blue dots. Those are the data that I get to see. But realistically, they were generated from green and purple. The latent variable associated with each dot is going to be, was it green or was it purple? And you can write down a model for this and make an inference about it. And it's a mixture model. Someone mentioned that earlier. You could do something that's maybe like my complete understanding of neuroscience that I've acquired over the past few days, where you posit some structure in the brain, maybe a cognitive map. I hear that's a thing, and then describe how the observations might be influenced by that structure. Neural data produced by traversing that map in some way. And models live on a spectrum that I like to talk about. Some models might be very mechanistic, so they are like actual physical processes, differential equations that describe like how molecules evolve in a mixture, or things that are just very, very empirical. Can I fit the data well with not a principled mechanistic understanding of it? But regardless of the model, the real question that I have is, how do you compute the distribution of the hidden structure given the data? And that's the posterior distribution. So the posterior distribution in terms of the model, which is the joint distribution of the data and the hidden variables, is simply that joint distribution, marginal distribution of the data. The model is given, and so we get to see that. And so you're like, why is this hard? Well, the challenge really lies in computing the denominator, which is that p of x. It's an integral over the model, but I have to average out over all possible hidden states. And there might be a lot of them. And in general, this high-dimensional integral, or sum, is going to be intractable. And so you're like, great. I told you that you can model stuff. You want to compute the posterior. It's hard, so maybe we're just going to stop. But instead, that's where variational inference comes into play. And what is variational inference is you take a family of distributions over hidden structure, Q of z, has some parameter lambda. And this is just indexing the variational approximation. And this big space here, this big circle here, are all the variational approximations, and different points are just different choices of lambda. And what you'd like to do is you'd like to find a lambda in this space so that the Q, the variational approximation, is close to the posterior, which is that point outside the space over there. And in what sense of closeness? Well, we need some sort of measurement for two probability distributions, and the one we're going to rely on is the KL divergence. But again, unfortunately, the KL divergence is intractable because it's the KL divergence between the variational approximation and the posterior, and we don't have the posterior. So the way to get around it is actually you can pull out a constant and find that maximizing this object here, called the evidence lower bound, is the same as minimizing the KL divergence. But you can get an intuitive understanding for exactly what's going on here. One way to look at it is the first term in this evidence lower bound prefers the variational approximation to find the hidden structure that makes the entire likelihood highest. While the second term encourages entropy. It wants the approximation to be spread out. For now, I'm just going to talk about mean field approximations, which means that there are going to be some independence assumptions in the approximation, but all the algorithms that we'll see will be more general than that. Another way to look at it, and this is just rewriting the same objective, is in terms of maximum likelihood. So if we look at this first term here, this is the probability of my observations given the hidden structure. And if you just had this first term, you try to find the approximation that makes my data most work. Try that. And you want to the way that the second term, the way that it influences the approximation is you want to regularize the posterior so that it's close to your prior beliefs. So how do we do variational inference? Well, we start with the model. It's a joint distribution over hidden structure and data. Next, we need to choose a variational approximation. You'll generally choose it so that this distribution is parameterized over the hidden structure I'm looking for. So if it's a mixture model, every single data point will have a mixture component. So these will just be categorical variables. Then we write down the elbow. This is just the objective we saw earlier. Log p of x comma z minus log q of z with parameter lambda. Then we want to be in terms of our parameters that we're optimizing over, so we compute the expectation. So just to see that again, I want to compute this expectation here so that my function is explicitly in terms of lambda, so I can optimize it. And this is just a toy example. Let's just assume that it's x times lambda squared plus log of lambda. Then you do the standard process. I have an objective. I can take derivatives. And then you could optimize with gradient ascent or stochastic gradient ascent. And if we were to see this all in a picture, what we get is a model, an approximation, an integration step, which is computing the expectation, some kind of derivative to help me optimize, and then this trajectory, which I follow the optimization algorithm. And we can do it for a model. So this model is the graphical depiction of a topic model. Here you have m documents, each with n words that you get to observe. Each word has a topic component indicator, so which topic does that word belong to. Each document has a proportion of topics, so like, is this document 60% sports, 40% news? And then there are topics themselves that are shared across the documents that tell you for each topic what word is going to be likely. And we can carry out this procedure. And you know, for many, many pages, this will continue. You get an algorithm, like one equation here. This looks like something you can program. You have phi and I is proportional to an exponential of some difference of digamma functions. But this is kind of a nice case, actually, for what it's worth. We can think about a simpler example, which is Bayesian logistic regression. So does everybody know logistic regression? Yeah. Okay. So here I have data pairs that are a label and some covariates. Xi are the covariates, y are the labels. And I have some regression coefficients. The way it's going to be Bayesian, or really just Bayesian analysis, is that I'm going to place a prior over my regression coefficients. And so this is the standard logistic regression setup where I have some regression coefficients. I generate the probability of my observation as multiplying those regression coefficients times my features, mapping it through the sigmoid function or the logistic function. And we can make it even simpler. We're going to assume we only have one data point. X is a scalar. And we'll choose a nice approximating family where we know lots of facts. Like the normal distribution, we know lots of facts about it. And in this case, the evidence lower bound, just following those steps, is a function of the mean and the variance of the approximation, is the prior term plus the likelihood term minus the entropy term, or plus the entropy term. And we can follow our recipe. So we start with that first step. Take some expectations. So this is probability z is a normal distribution. It's something like expectation of z squared. And so you'll get the mean squared plus the variance. This is the entropy. Wikipedia can tell us that. And then we have an extra term here at the end. And I'm dropping constants. And so we can expand out that extra term. This is just the Bernoulli distribution's probability. Okay, go ahead.
Is there a way to evaluate how closely your variational approximation to posterior approximates?
That's a good question. If you can ask me that at the end, I'll try to answer that one. But it's generally a hard question. And then we can take this expectation here because we know it's Gaussian. But with this last term, we're stuck. And by being stuck means that we can't analytically take that expectation. There's no nice mathematical form to do this. And we need to do it because if we change the parameters, the value of this expectation will change and the objective will change. What we'd like instead would be a framework where we don't have to go through those steps, do model-specific work. We can take in facts about variational families. We can take in any model, a data set, and get an approximation to the posterior. So why did we run into trouble? Where was the trouble in the classic recipe? Well, we were able to write down a model. We chose an approximation. But we got stuck at integration. And we couldn't go any further. So the solution, like a lot of machine learning solutions, will be just to swap the orders of those steps and write the gradient as an expectation with respect to the variational approximation and use stochastic optimization. So how do we take gradients of expectations? So we have some general function, g of z and lambda. Z is the variable, lambda is a parameter. And I want to take the gradient of that evidence lower bound. And the way that I take the gradient is simply gradient of the integral, expanding it out. Then the next step, I'm going to interchange the derivative and the integral, which you can do under some technical conditions. and then just follow the high school product rule. That's what that is. Then in the next step, the second term is already an expectation with respect to q. And so I'll just keep it as is. But here I don't have a q, I have the derivative of q. But you know that the derivative of q is equal to the derivative of log q times q. It's just the derivative of log, as right here. And then now I have q on both sides. And so I've generically wrote the derivative of an expectation as an expectation itself. Meaning that the way to compute something like this would be to take samples from an approximation and then average this. So we're going to see a couple of examples of this and then how to make it a lot faster at the end. So we have this generic form for taking derivatives of expectations at the top, but we can plug in our evidence lower bound and ask what happens. So for that second term that's up there, the second term will disappear because we have the fact that the expectation of the gradient of log q is equal to 0. If that's not transparent, that might not be transparent. All right, we can see it. So you have the expectation with respect to a distribution of the gradient of log of that distribution. Okay. And now, just to make things nice, we like to rewrite things as integrals. So this will be the integral of q of z with parameter lambda, the gradient with respect to lambda of log q of z with parameter lambda. And this is integrating over z. I can reverse the same trick that I had earlier to replace the gradient of log with the gradient times divided by q. So this is equal to the integral of q. I'm just going to drop the inside notation times the gradient with respect to lambda of q divided by q dz. And this is equal to, these things cancel out. This is equal to the integral of the derivative with respect to lambda of q, just from the cancellation here. And then now I'm going to swap the derivative in the integral again. The integral of q. But can somebody tell me what the integral of a probability distribution or density is? Is 1. Yeah. So this is equal to just the derivative of 1, which is equal to 0. And so you can use that here, and then you can get an estimator for the gradient with respect to the evidence lower bound. It's simply the score function times the instantaneous elbow. The same gradient is used in reinforcement learning, and that's why it has a name called reinforced gradients. It's used in finance as the likelihood ratio trick. I don't know did anybody talk about policy gradients? Yeah, so policy gradients are a way to do reinforcement learning, and they follow exactly the same form. And the way that you get an estimate of the gradient is you may take a bunch of samples of your variational approximation, you evaluate your model, you evaluate the variational approximation, you multiply by the score function and average. And you get a pretty simple model. Instead of doing pretty simple algorithm. Instead of doing pages and pages of algebra, now you have something that will fit in a couple lines. You draw some samples, you choose a step size, you compute the average gradient, multiply it by the step size, update your parameters.
I always thought you want to do variational inference when you don't want to do sampling.
Well, there's a difference between Monte Carlo sampling and Markov chain Monte Carlo sampling, and I think that's the key difference. Like sampling, like if Q is a Gaussian, for example, or just a transformation of a Gaussian, it's really easy to evaluate, meaning that I can do it, I sample a Gaussian, I pass it through a function, I have a sample. Well, if I'm running Markov chain Monte Carlo, I'll have to wait for it to mix. But the distinction between the two are quite blurry. Like you could embed a Markov chain Monte Carlo algorithm inside of a variational approximation, or optimize a Markov chain Monte Carlo algorithm with the variational method. And so what are the requirements for doing this? To compute the noisy gradient, we need to be able to sample from the approximation, to be able to evaluate its score function, to be able to evaluate the model, and its variational approximation. And there's no model-specific work. Our criteria for being able to just specify a model and compute something, not clear how accurate it is at least met. But the problem is that you can implement that, but it will take a really, really, really long time for it to get the answer. Like it's theoretically sound. And that's because when you're doing stochastic optimization, the variance of your gradient matters a lot. Meaning that if somebody tells you exactly where to go to improve your objective, you can follow it a lot, you can trust it a lot. But if somebody injects a whole bunch of randomness into it and you go too far, you won't be able to figure out if you've done it correctly or not. Or you'll need to ask many, many questions to average to be sure about where to go. And one solution to that is to use control variates. And this again appears in the reinforcement learning literature. The basic idea is that if I want to compute the expectation of a function, I can replace it with another function that has the same expectation, but might have lower variance. So if I have a function f of z that I'm interested in, f hat of z will have the same expectation for any value of a, because this thing has expectation 0. Okay. And as an example, the more knowledge I have about the distribution and the function I'm taking, the lower the variance it has. So if my original function is f, has a lot of variability, if I use the knowledge that I know what the expectation of x squared is, I'll have something that looks a little bit less variable. If I know the entire function, I'll actually just get a constant, where a single sample will be enough to tell me the expectation. And for variational inference, you want something that's pretty generic. You don't want to limit yourself to a specific model or an approximation. And the way you'll do it is just to use that fact that's on the board. Because what's on the board says, for any q where I can do this interchange, the expectation is 0. And what that means is that this provides a control variate, because it satisfies that property up there. And there are lots of new things that have come along here to really scale this along. But they mostly come from Monte Carlo, whether it's importance sampling, quasi-Monte Carlo, or computing conditional expectations. And with this, you can build like a whole slew of models. Like all the models here, you could run with this. I think most of these actually have been run with this method. But I think what's nice about it is like you can really design models for data rather than based on what the computation you have is. And that's a change, like if you were to pick any of these before, you would do those pages of algebra, and you might write a paper because you've committed yourself so much after doing those pages of algebra. So we're going to mix it up a little bit here at this point. What if we throw in a couple more assumptions? So our current criteria are that we can sample from the approximation, we can evaluate the score function, evaluate the model, and its approximation. So can we make additional assumptions that are not too restrictive? Well, the typical machine learning one is going to be differentiability, and that will lead us to something called the pathwise gradient of the elbow, or the reparameterization gradient of the elbow. Okay, so the couple of assumptions we'll need, one is we're going to assume that for our variational approximation, we can write it as a function of some noise that's sampled from a parameter-free distribution. And this function can take in the parameter and should take in the parameter as well. And so specifically, if I have a sample for my approximation, another way to do it would be to sample some noise, pass it through this function, and look at the evaluation. An example of this is that if I want some variable that is mean, mu, and variance sigma squared, and normally distributed, I can sample a normal distribution without any parameters, so mean 0, variance 1, multiply it by the standard deviation, and add the mean. And the second thing I'm going to ask for is that my model and my approximation are differentiable with respect to the hidden structure. So that would rule out something like a mixture model. And so once I have this, I can start from the top again, use my generic gradient form. This is exactly the thing that we computed by pushing the derivative inside the integral and then using the product rule. And then I can rewrite it using the fact that I can know that z is equal to some function of some noise and the approximation. And this rewrite is really just a change of variables on the integration and gives me this form here. To simplify it again, well, we can use the fact that if I take the derivative with respect to something that doesn't have the parameter, it's going to be 0. Because there's no lambda in S of epsilon. So this will be 0. So this term will go away. And so I just have the second term. And then the way that you'd use the second term would be to just use the chain rule to differentiate this. So you know that z is this first term. So you can ask yourself what the gradient with respect to the instantaneous elbow is with respect to z, multiplied by the derivative of the inside term, and then multiplied by the direct derivative of the inside term is the score function. And this is known as the reparametrization gradient and has a long history in Monte Carlo as well, too. And so to compare and contrast the two methods, I have one method which differentiates the density. Really, you're differentiating the distribution Q, while another method differentiates the function itself that I'm interested in computing the expectation of and maximizing. The score function works for discrete continuous models. You don't really have to think about it. But the pathwise estimator requires differentiability. This, again, works for a large class of approximations. This requires a limited class of approximations, specifically ones that have this transformational form. This has been relaxed. They're like implicit versions, which means that you don't need the transformation explicitly. You can have its inverse or other things that let you have access to its derivative. But the key thing is that here variance can be a big problem. But for the models that you typically fit, the variance will be well behaved here. So now I'm going to talk about how do you actually do this at scale. So this is a very large hierarchical model. So here I have n data points. Each of these data points are shaded, and so they're observed. They're xn. For each of these data points, I potentially have a latent variable associated with it. Could be a mixture, could be a factor component, could be some topics. And then there are things that are shared across all the data that help me generate both the local latent structure for each individual data point, like the mixture of the topics, or the data itself. And we have an approximation, which says that if this is our model, you're going to choose a very simple variational approximation where everything is factorized. And we can get an algorithm now that's like super scalable using the same principles. So if I have a model that's a joint distribution over global structure, local structure, and data, I can choose some variational approximation parameters randomly at initialization, pick a learning rate, and instead of using all of my data at once, I can sample a single data point, find the best local approximation for that data point. That's what this line is. And then set the global parameter based on the derivative using the best local approximation. And then this thing now, instead of at every step using n data points, only needs a single data point to update. But again, we have a problem. So like the traditional approach to scaling variational inference, everything here would be tractable. This maximization would be one line of code. But now, because the expectations and the maximizations require Monte Carlo sampling, require following gradients, you really need stochastic optimization for every single data point. So it becomes slow. The solution to this is going to be really learning a mapping, just we'll call arbitrarily f, from each data point to its optimal approximation. So you're like, instead of just learning the model, you're also learning how to do inference. What that means functionally is this is just my evidence lower bound, where I have a model term and approximation term, is that what you'd like to have is you'd like to have these local parameters, these local variational approximation parameters, be functions of my data with a shared global parameter. There's a missing log here and here. And so once you have this, you have a very different algorithm. Instead of having to do maximization for every single data point, so meaning that when a new document comes in, you figure out what the topics are. When a new data point comes in, you figure out a mixture component, its factors, it's like deep codes. You can actually just jointly optimize. You optimize the variational approximation, and you optimize the approximation that is learning to do inference for you. But again, there's a trade-off. So this kind of inference, which we call amortized inference, because you're learning this function that learns how to do inference, is much faster, because you take in a data point, you get an approximation. But it's inherently smaller, because this family here, all these values of phi I are not tied together. But for this other family here, where you've amortized, they're inherently all tied together because they use the same function. As an example model in this class, or in this class of models, is the variational autoencoder. So what the variational autoencoder is, it's a simple nonlinear factor analysis. That's the way you can think about it. You have a normal variable, that's a vector. It has some dimensionality, say 2, 10. It's something that you might need to select. You take that variable, map it through 2 neural networks to get the parameters for your data. So this is the mean, this is the variance. And then you generate your data condition on that value. So to turn it into something like factor analysis, these functions would be much simpler. You'd have a linear function that multiplies it across and possibly fixed variance. And to fit this model, we're going to use an inference network. So you have a forward process, which takes a latent variable, some abstract d-dimensional representation, passes it through a model. You get samples of your observation. And you have a reverse model, which is the amortized inference or inference network that takes in data and gives you a distribution on the latent variables. And the way this works is also with neural networks. So the mean of the variational approximation is the function of the data, and the variance is also a function of the data. And these things do reasonable things. For example, if I have a bunch of digits, I can really corrupt the digits massively, and then I can simulate from both the model and the inference network back and forth, and do a pretty good job of cleaning them up. You can also do funny things. I haven't thought of an actual use for this, but you can take 2 digits in their latent space and try to interpolate between them. I think people have done this on much cooler images than digits. They do it on like faces to get your combination of like yours and Barack Obama's face. But all the technology to do it, we saw everything. If you have differentiation, you have neural networks, you have a latent variable model, that's all it needs to do this. And one thing I'll say about latent variable models and general fully probabilistic models is that they really do try to answer every question for you. They answer like an interpolation question, a denoising question, and that may seem cool, but you do pay a cost for it. Because if you had a specialized approach to just do this, it's probably better than an approach that is consistent for everything. Now we're going to get a little bit annoying. It's getting towards the end. Let's just assume that we have just a bunch of fMRI and responses for people. So the fMRI are just these bold X's. I is the index of a sample, or is index of a person, N is the index of a sample, and I have responses associated with it as well. And just the abstract goal is to understand how each of the X's relates to its corresponding Y. All right, this sounds simple, right? Like we can just do regression because it's, I have inputs, I have outputs, and I can just regress x to y. But I have a question, and maybe you all can help me out with this, is should I do one regression across all of the subjects, or should you do one regression for each subject? Like, both of these are valid ways to answer this question because I have multiple data points per subject. But then if I have data from other subjects, it might help me share some kind of strength because people look similar. But what is it? Does anybody have an opinion on this?
Isn't that why you use like a mixed effects?
Yeah. So a mixed effects model would be something more general in one way that I'm going and slightly less general in another way that I'm going. But a simpler approach would be like just like a multi-level model or hierarchical model. So if I have like specific, if my mixed effects are only hierarchical, they would look very much like this. So one way to do it is that, you imagine regression for a subject with I has some generic parameters beta I. And I have some function beta I that will take an xi and produce the mean of my regression, and then I'll just assume that the variance is 1. And we're just going to adopt a Bayesian analysis for this to just see how like simple the ideas are. So how we do Bayesian analysis is we just place a prior over beta I, and that prior, just for simplicity, is just going to be normal 0, 1. And once we have this, we can do Bayesian analysis with this pipeline, and we can do it with some probabilistic programming languages, Stan, TensorFlow probability, or Pyro. And once we have the specification and some data, it will really do the rest for us. But we could also just modify our model. Suppose that we have some code, and the way that code would be is that I still have the same likelihood function, but I'm going to change my prior for each of the individuals to not be drawn from normal 0, 1, but instead to be drawn from a normal distribution with mean beta and some parameter tau I. And then this new parameter that I've introduced, beta, is going to have a normal 0, 1 prior. Okay. And again, I've changed my model a little bit, but I don't really need to change my analysis. With Stan, TensorFlow probability, or Pyro, this thing would just run, be a one-line code change. And to see that super explicitly, this is actually the Stan code for hierarchical regression. Here you have d dimensions, you have L groups, you have some parameter that is shared across the groups, and for each of the groups you get a beta, which is a regression coefficient, and this is just doing each dimension separately. And then at the end, I generate the data, or they generate the data, and you have a Bernoulli, which is just the 0, 1. You have the way you compute the parameter, which is just taking your features, covariates, multiplying them by the beta for the group of this observation. And Pyro and TensorFlow probability guides have examples that are like this as well too. But why does this help? And this is going to be probably the most annoying part. Save the best for last. So you can think of a simple case with just endpoints. And then we can do the linear setup, so we don't have to worry about the other parts. And we have that yin is just going to be normal with beta I transpose xin with variance 1. And in this case, where I have a normal prior and normal observations, the posterior distribution is going to be normal with some covariance and mean, and these are the analytical forms for it. We can ask ourselves what happens when we have lots of local samples. Say that we have like a huge number. Then I should also say I limited myself to one dimension here. So x transpose x is really just the concatenation of all the observations for that particular group. Well, if I have more local samples, then x transpose x is just a bunch of numbers that are greater than 0 being added together. So it's going to start looking big relative to a constant, which is tau I inverse. The other thing that happens is x transpose y, again, is a sum of a bunch of numbers. And it will start looking big relative to the inner term here. which is tau inverse times the beta prior. And so what happens is that when you have a lot of observations is that this thing gets very, very close to just doing linear regression inside the group itself. When you have no observations, if you look at the form of the posterior, well, this term is 0, this term is 0, and I get exactly the prior. And the point of this really is that the posterior deviates from the prior with more data within each group. And that's true for it doesn't matter what the model you're building is. I could do hierarchical topic modeling. I could do hierarchical variational autoencoders. It's just a really simple example of that concept. And you can place priors on Ti, or tau I should say. And those priors will control how much each group affects the overall group estimate. So here's some general advice that I'm going to end with. So if you want a rule of thumb for a new model, you can see if your model is differentiable. If it is differentiable, choose an approximation that is reparameterizable. If it's not differentiable, you can try the score function, maybe reduce variance or take some continuous relaxation. That might help you further. You want to set learning rates using modern learning rate tools like RMSProp, Adagrad, or Atom. You can parallelize your computation across samples for speed, and you might want to use some techniques from physics to help with the optimization process. Sounds great, right? Sounds really simple. Better advice. Start with some software. Don't do what I just told you. And this is really like a change. If you're trying to do this stuff 6 or 7 years ago, you really would have to follow that process. You'd have to figure out your model, figure out the approximation, do a bunch of math, code that up, hope it works, see if it converges, and then maybe you have something. But now people have taken what I've talked about and implemented it inside tools that are accessible from Python, where you can specify your model. I think Pyro, somewhere here, it was on an earlier slide. Pyro has a guide which chooses the variational approximation for you, and so you really will just get an answer straight out. And it has backends of GPU computation, so it's much simpler to use than before. And I'll take any questions, and I have a question if nobody has questions. Go ahead. So control variates are a way, so you have the expectation, you want to compute the expectation of a function. You can write down another function that has the same expectation, but it might have different variants. So control variates are a way to create a whole family of those functions and to choose the one that has lowest variance. Generally, the way it works is to subtract an expectation 0 function.
So in clinical data, there's a number of subjects and there's a lot of voxels for every subject. But in experimental data, there's a couple of conditions and there's some data sets, which is time series of things that subject did, and these are much less compared to the number of voxels. So I'm wondering, in which situations would you use one or the other of the approaches? Because usually, I guess, a lot of...
What are the two approaches that you're talking about?
So one is every subject has a very large number of voxels, so there's a lot of data for a given subject, for instance. The other thing is you have, it's not that you're comparing anatomy, you're comparing the functional data, which is behavior that they have. The number of sampling of these behavioral conditions is much lower than the number of voxels to which you're mapping this. And then the number of subjects is not very high either. So what would be the optimal kind of...
I mean, my answer would be that you should let inference take care of that, depending on what you think your likelihoods are. Because choosing one or the other, it just depends on how accurate you are. It could be that if I know a single person, then I'm in this really special, I have the best theory ever, and so it's perfectly predictive for every other person. And then inference would tell you that, your posterior for the groups, even though you haven't seen data, should be super concentrated. But in general, I think that these questions really, the way you pose it is exactly why you'd want to do inference over it, because I'm not sure beforehand.
Is there some category that is known to overfit, or one that suffers more from an inadequate number of data samples, one that is better for large data?
I mean, I think if you have large, I mean, I think computation is really where you'll feel the difference. Like if you're going to do inference over just doing maximum likelihood, which we heard about, maximum likelihood can be faster. And so if I have a large data for a single observation and I do maximum likelihood there, it will be faster. But in terms of overall quality of the inferences versus and overfitting, I mean, certainly if you place priors, you can overfit less, but you could also regularize your maximum likelihood approach. And I think the answer to that is always held out checking. And I think that's my answer to the earlier question about like, what's the quality of a variational approximation? Well, you're going to hold out some data and you'll ask yourself, this model plus this variational approximation, how well does it predict my data? And in general, for a lot of things that we have with hidden structure, it will do as well as possible because we just don't know how to run Markov chain Monte Carlo algorithms for things like big variational autoencoder as well.
Do you have any opinions about which of the Python probabilistic programming libraries you're using for different tasks? Because it seems like every time I look,
Yeah.
three new.
Yeah. Yeah.
Are deleted.
Probably, I mean, Stan is the most heavily used. Like it's like if you're doing like hierarchical regression, it's the thing to do, but it can be slow. Like it doesn't have like the support of like Google or Uber engineers in the backside to make it super fast. And so if you can do it in Stan, and Stan has a Markov chain Monte Carlo algorithm implementation that's amazing, I would do that. But then I would back off to either the two things, Pyro or TensorFlow probability. The other programming languages, probabilistic programming languages, are cool, but they tend to feel more researchy than actually like for someone who has a model and they want an answer.
The advantage of STAN is that a lot of people in psychology and neuroscience are familiar with it compared to the other ones. And the advantage of TensorFlow is if you're sending it to like more computer sciencey sort of or deep learning places. So STAN is like I feel like now a little more used.
But slower.
Yeah.
Yeah, it's noticeably.
Any other questions?
Oh.
We can wrap up.
I'll ask my question before I'll ask my question for you. Yeah, I mean, listening to everything that I've seen so far, you know, my feeling is like, how do I choose a model is a question that comes up to me. Like I can build a model and then that model will predict well, and maybe it's the best possible predictive model I can have on held out data, or I could analyze my data, look at statistics from my data, and then correlate those statistics to something that I care about. And my question is like, should I favor one over the other? Because like, if I'm going to believe a theory, shouldn't the theory be most predictive? It's just a question.
What were the two options you had?
It's like something that is like, you don't know exactly how it works, but it gives you the best prediction possible on your held out data. Another thing where you're like introspecting into the data, maybe pulling out first or second order correlations, and then looking at how those correlations predict something or decode something. I think that's the right word. And the second thing, by assumption, with the way I constructed it, works less well than the first thing. But you know, should I have trust in the second thing if it works worse than the first thing in terms of predictions? And meaning that if I have a theory, and that theory is in two models, one is just something that's very complicated, the other one is just like easy to introspect, and one is more accurate on held out data than the one that's easier to introspect, should I trust the introspections? Yeah, go ahead.
Maybe I could take an attempt at translating this into
Sure.
like cognitive neuroscience. So on the one hand, not for like on the one hand, you want a more like biologically plausible and or simpler model that doesn't predict as well, or do you want a super complicated model you don't understand that predicts really good?
But you can introspect on it after the fact.
Right? Okay.
Yeah, like you're not necessarily building it into the analysis pipeline.
So the problem with the second option that you're saying, if it's not biologically inspired and you can't test it at multiple levels, is that it might work at some point in time, but it wouldn't work for the rest of the things that it needs to fit with and all the future sort of studies or different kind of experimentations or connection to other parts of the brain or connection to other kinds of experiments. Which is why if you want to test something from, for instance, let's say reinforcement learning, that the discovery of dopamine prediction errors made a huge difference in their relevance.
Mm-hmm.
Because then there was something basic that they could anchor to And then in other parts of the brain, it was possible to see, okay, what correlates with this? And is there something that correlates with that? And then it was possible to build up from that, and reinforcement learning as a framework became valid to be tested in these kinds of biologically plausible ways. But then someone might just make a horse race between a bunch of different reinforcement learning algorithms, and one of them might explain some behavioral data better. It doesn't mean that that's how the brain does it, right?
Well, I believe that, but I think like using a model to because like you fit a model sometimes to understand how the brain does something, but then you should only fit models that are plausible based on your understanding of how the brain does something. Feels like I'm in a difficult situation. Because like if I want to use the model to find something new that the brain might be doing, where does the information I have come from to make it biologically plausible? I don't know. I've just been listening to talks, and this is just an honest question that
It's
I'm
like
wondering.
a Lego. You make
Yeah.
an inference on the basis of putting this part and that part, and design an experiment that tests that. And this is how, for instance, things like internal cortex or grid cells or all of these things, that's how they happen. Some of them by accident, to be honest. But some other times there's something that the experiment, that the model predicts, and you need to set up an experiment to just test whether that's the case or not, which is what, for instance, we did in a bunch of our studies. The model predicted something, there was no study to distinguish between some things. You design explicitly something, a study to
Test that without any modeling inside of it.
say again.
Like when you design that second study, you test it without any model inside of it.
I don't understand.
So like you use a model, you form a hypothesis, then you design a new experiment to test that hypothesis, but this testing of the hypothesis doesn't rely on the models that were previously created.
Well, it compares them. You explicitly design experimental conditions that would be different for the different models. So you know that the both models are going to explain a bunch of behavior equally well. You go and find some range of behavior where these models would disagree on. And for that, you first do a simulation and see where would these disagree on, and then design a study that tests exactly that part where they disagree. So that in that way, that's how some of us do. Some people do more experiments.
Well, that's rejecting a model with hypothesis testing. That I would believe in. But anyway, talk about this offline because it's just the two of us now.
But I think maybe Luke, you might have some other perspective because you're more data driven.
I think it just depends on what your goal is. Like sometimes, like for example, if you're doing imaging data, you might want to have a model that's like as accurate as possible detecting like anomalies in your data. You don't really care how it does as long as it works really well, and so that's useful for certain things.
Yeah.
And other times you want to create a model because you're trying to test some psychological hypothesis or neural hypothesis that how something works. And that I do think you want to be able to introspect or interpret it. And even if it's like really, really simple and oversimplified in how it actually works in the brain, I think it's looking useful to kind of leverage up and get closer to how the process works. But I don't think there's like a fast and strong rule personally. I don't know, Jeremy, if you feel that.
I would agree.
Maybe one thing for everyone who was also yesterday at the other workshop. Two different kinds of models that are discussed in cognitive neuroscience are normative and mechanistic. People might have heard it, and there are sometimes debates about them, or you might see them in papers. One cares about how it's done, one thinks about how it should be done, and doesn't as much care about the mechanisms. So you could have a more normative model or see which model works best and come up with a normative model. You don't have to worry too much about mechanisms there. Or you might want to have a mechanistic model, then you really care that actually this is sort of simulating the mechanisms. And in that way also, I think that even in this top-down approach, there's a difference in those two approaches.
Actually, now that you say that, I'm going to revise my. So, like, the best model maybe is like a perfect simulation of the brain.
Mm-hmm.
I agree.
And then, so if we had that, it would like necessarily be as complicated as the brain,
Mm-hmm.
and wouldn't really teach us. Like, you might as well just ask a brain what it's doing, and ask someone what they're thinking, rather than trying to decode it, because we already have brains.
Like the Lewis Carroll example from yesterday.
Yeah, right. Like, why make them not the same size as the world, or England, whatever? I forget. But then on the flip, so that extreme is probably too far, and then maybe like regression or something like that is the simplest model, and that's nothing like the brain. So we can really get neural insights into using regression.
I mean,
it's also just not the case that the data generating process will actually be the best fitting model for the data. Like you could, in theory, know exactly what was causing your data, but it would not necessarily listen to like the best model for statistics, the best out of sample prediction, which is problematic if all you're basing your goodness of the model on is like how well it's predicting. So if your goal was prediction, then fine, predict. It's you're solving your goal. There maybe are stationarity issues over time, like Ida was pointing out, that like if the world changes, it might not work anymore. But if your goal is to like recover the data generating process, then relying only on model statistics is not going to necessarily get you there, even if things are perfect otherwise.
Yeah, in addition to that, since Bob is not here, right? Since Bob is not here, I'm just going to repeat something he said yesterday. So there was a situation where the model that was best fitting the subject's data when it was generating the result was, remember what he was saying? It couldn't solve the task. But so it meant that they had a bunch of models. Some of the models solved the task on their own, some of them didn't. And the one that best fitted the human behavioral data was the one that actually couldn't even solve the task, so it wasn't the best model. And they realized that, okay, we don't have the right model that is capturing the right kind of variance. But making sure that both two sides are there gets you to this point where you realize that not only is your best model not the best in terms of explaining the behavioral data, but your best fitting model can't even solve the task, so it's not even good enough. So these are the situations where it's important to look at both how the model behaves on its own and which one fits the data better, just to make sure that you have something that plausibly explains the data. So in that case, that was a fail. Clearly, none of their models was good enough for explaining human behavior.
Yeah, I mean, to address that point, I mean, I think that's certainly true. You can construct non-parametric estimators and they'll be perfect predictors, and they'll have nonsense when it comes to actually understanding something. This point, interesting. I don't fully understand it, but we can talk about it later. Yeah.
Let's wrap up.